How you doing? You good? All right. Pardon me? I have not finished marking it yet. I am like halfway through.
You have 3 days.
Yeah.
Oh, you have 2 days actually. It's Prody Day. You have to.
I have 2 days.
Sad.
Okay, folks, we are on page 30 and we're starting right away so that we can get done by the end of class and get out of here for your lovely long weekend coming up. So we're talking today about saturated and unsaturated solutions. Have you heard of them before? Yes, very good. So hopefully you know that an unsaturated solution contains less than the maximum amount of dissolved solutes.
Why are you looking at me like that?
So, if there is undissolved solute present, and we haven't and it hasn't been a long time, we haven't been stirring it for a long time, it's really hard to phrase this because what I'm trying to say is we are in the process of dissolving, yes? And we haven't been stirring long. We are in the process of dissolving. If that is the case, then the system is not yet at equilibrium. And what we've got is we've got some solid, okay? And you can see the red arrows. On your page, I've made them dashed so they look different than the black ones, but I'm going to make these ones red here. So our red arrows show the dissolving. And you can see that there's 1, 2, 3, 4, 5 dissolving. And only 1 recrystallizes. It's supposed to be a Z. Are we at equilibrium? No. And are we saturated yet? No. So basically, if the rate of dissolving is greater than the rate of precipitation, so if the rate of dissolving is the bigger one, then we have an unsaturated solution. We can also look at this from a reaction, like sort of using reaction arrows. So if we put some solute into the solvent, the moment you put it in, the rate of dissolving is very high. But the moment we put it in, the rate of recrystallization is 0 because we don't have any dissolved ions yet, correct? So that is in the moment you put that solute into the solvent. Dissolving is high, but you got no ions yet. Therefore, the reverse rate is equal to 0. Now, as time goes on, you are going to dissolve some of the solid. And so these concentrations get bigger, yes? However, we still have a forward rate faster and the reverse rate, which is slower. And if that's the case, are we saturated or are we unsaturated? We are still unsaturated. Yes. Now, eventually, it's possible, if I just take a teaspoon of salt and I dump it into the water and I stir it around, it's eventually, I might just run out of solute, right? It might all dissolve and I might not have any solute left. Okay, so if we run out of solid solute, then the solution is unsaturated. It's not at equilibrium because there's no solid. Okay? That's if we run out of the solid solute. Or we can get to the point if we have solid solute left, but the rate of dissolving is equal to the rate of recrystallization. So the forward and the reverse are equal. What kind of a solution do we have now? This is now saturated. So you're either, if you dump in some solute, you stir it around, you're either going to get to the point where you dissolve all of it or where some of it remains undissolved, but it's at equilibrium now with the solid. Yes, those are your two options. So if we run out of solid, we have an unsaturated solution. But if we get to the point where the rate of dissolving equals the rate of recrystallization, we have a saturated solution. And whereas unsaturated it contained less than the maximum, a saturated solution contains the maximum amount of dissolved solute. If we have undissolved solute present, and we've been stirring for a while, so it's had enough time to dissolve, then the system is going to be at equilibrium. And you can see in the picture, I have my red arrows. Now I have 3 dissolving. 1, 2, 3 red arrows. And I've also got 3 black arrows. 3, 3. Crystallize. What is the concentration going to be like if the rate of dissolving is equal to the rate of recrystallization or the rate of precipitation? What's going to happen to the concentration of that solution? Concentration stays the same. Okay, we are at equilibrium. So a saturated solution, pretty much by definition, is at equilibrium. Now we're going to take a look at a couple of methods of making saturated solutions. And the very first one is the easiest one. It's the one you just take some water and you dump in your solute. You know, here I've got some copper sulfate and I got my water and I'll just dump it in and I'll stir it around until what? Until some of it won't dissolve. Okay? This is why I call it the dump and stir method, because you dump in the solute and then you stir it. And then you just keep doing that until you have some undissolved solute staying there, even though you stirred it for a while. Okay? So that is our dump and stir method. Now, when you dump in your solid, let's say we had some solid calcium fluoride, CaF2 solid. When CaF2 dissolves, how many calcium ions do we get? We get 1 calcium. And how many fluorides? 2 fluorides. So if I'm dumping calcium fluoride into the solution, I have a 1:2 ratio. And you can see that in my little beaker here, I have 2 calciums. And I have 1, 2, 3, 4, 5. Whoops. I have 3 calciums. 3 calciums. 3 calciums. There we go. That looks sad, but that's okay. 3 calciums, and we have 6 fluorides. So again, that is a 1:2 ratio. Okay, so when you create a saturated solution by using the dump and stir method, you get a 1:2 ratio. The ions are proportional to the coefficients. Okay, so over here, if CaF2 sat, that means saturated, is 2.0 times 10 to the minus 4, what is the concentration of calcium? Same thing, 2.0 times 10 to the minus 4 molar, and fluoride is 4.0 times 10 to the minus 4 molar. And remember, we always write the solubility equilibrium equation, the C, with the solid on the left. And remember, that's different from the precipitation equation, the PE, where the solid is on the right. Okay? Here's a second definition of a saturated solution. Let me know, did I move too quickly or are we good? We're okay? Okay, good. If I'm ever like scrolling too fast, just say, go back, or raise your hand or something, okay? In a saturated solution, it is a solution in which the dissolved substance is in equilibrium with the undissolved substance. So our dissolved substance is in equilibrium with some undissolved substance. And we can actually make this happen without dumping and stirring. Do you remember earlier this week when we took some iodide ions and we mixed them with some lead ions, and we got that brilliant yellow precipitate? Do you remember that? What happened there was our precipitate was PbI2. If we get a precipitate, that means that the solution was saturated with lead and iodide ions. Yes? So if a precipitate forms, the solution had to have been saturated. It means there's not enough room in the solution, in the water, for the rest of those ions, so they came out as a solid. Now, the concentrations that we used 0.1 molar I and 0.01 molar lead. Now, PbI2, there's 2 I's for every 1 Pb. Are the concentrations of lead and iodide 2 to 1? No. And the reason for that is that our lead came from a solution of lead nitrate, which was mixed up to be at 0.01 molar. And the iodide came from Ki, and we mixed up that solution to be 0.1 molar. Okay, and we created lead iodide by mixing those 2 different solutions. And so this particular method of creating a saturated solution, I call it mix and match, because we mix the 2 ions from different sources. We mix 2 different solutions. And then the ions match and form a precipitate. Yeah? So you mix the 2 solutions and you get a precipitate. And if that's the case, if that's how you make your saturated solution, are the ion concentrations proportional to the coefficients? No. All right? And I'll keep reminding you of this because we get so used to seeing the ratios being like 2 to 1, 2 to 1, 2 to 1, or 1 to 1, 1 to 1, 1 to 1, that it becomes weird to think that, oh, this one could be 10 times as much as that one. So I'll keep reminding you about it as we go. All right, so if we mix 2 solutions and a double replacement reaction occurs and we form a precipitate, so anytime you form a precipitate, we have created a saturated solution. And they will not be present. I mean, they could be, but they don't have to be present proportional to the coefficients. And now we're going to look at 2 examples that kind of prove this. And we're going to use totally unrealistic concentrations. Okay? So we're going to look at situation A over here, and then we're going to look at situation B. So situation A, we have some sodium chloride. And if you go through and you count, you'll find there's 8 sodiums and 8 chlorides. And I'm not really interested in the sodium because it's going to be a spectator. So I'm just going to say that I have 8 molar chloride. In my other beaker, I have 5 silvers and 5 nitrates. Again, nitrate is a spectator, so I'm going to ignore it. The concentration of silver is 5 molar Ag+. These are way larger numbers than we would have in real life, but we're just going to work with it here. Are the concentrations of chloride and silver the same? No. And now we're going to mix them together. So this is the mix part. We're taking our sodium chloride and putting it together with our silver nitrate. And they match to form a precipitate. Now you'll notice all our sodium are still floating around, all our nitrate are still floating around, all our spectators have done nothing. But remember, AgCl is low solubility. That means there's a tiny bit dissolved. AgCl is low solubility. But there is a little bit dissolved. And if we look, if we count, we used up all of our silver but 1. We have 1 silver left. And we have 1, 2, 3, 4 chlorides left. So our concentration of chloride here is 4 molar. And the concentration of silver is 1 molar. Are those concentrations the same? No. Is this solution saturated? If a precipitate forms, you are saturated. Yes? Because what it means is there was too much, and so it precipitated and only a little bit remains dissolved. Okay? So this is a saturated solution. Now we're going to look at a second scenario with different initial concentrations. Okay? Where'd you go? There you are. Okay. So now we're looking at situation B, where we're going to take, now we have, instead of 8 molar sodium chloride, now we have 6. So we have 6 molar chloride here. And we've increased the concentration of silver nitrate to 6 molar. So we have 6 molar silver. We are going to mix those together. And you'll notice, oh, what did we get? We got some solid. The silver and the chloride matched to form a precipitate. How many silver are left over this time? 2. So the concentration of Ag+ is 2 molar. How many chlorides are left? 2. Concentration of chloride is 2 molar. Is this a saturated or an unsaturated solution? It is saturated. Anytime a precipitate forms, you have a saturated solution. So this is a saturated solution. So you're going to be having ions coming off and ions reprecipitating, okay? Over here, you'll have ions coming off and you'll have ions precipitating, okay? So it is in equilibrium. Both of these solutions are at equilibrium. Since they are at equilibrium, we can write a K value for them, yes? Let's start by writing the K expression. Oh, actually, before we do that, it says to write the net ionic precipitation reaction. Who would the reactants be in the net ionic precipitation reaction, the PE? Tell your partner.
Spectators are spectators plus antenna ions that react are A and CL. Oh yeah, the reactant.
Who are the reactants in the precipitation reaction? The net ionic precipitation? Ag plus and Cl minus. This is our precipitation equation, and that is aqueous and aqueous. Now, do we use a one-way arrow or a two-way arrow for the precipitation? One-way arrow. And we get AgCl. And the reason is that when we're doing a precipitation, we don't really care that it's going to form an equilibrium later. And if it does form an equilibrium afterwards, which a lot of them do, we have to put the solid on the left. Okay, so next, we form the solubility equilibrium equation. So we get this precipitate, and then we get the solubility equilibrium equation. What does that look like? AgCl, solid, in equilibrium with Ag plus Cl minus aqueous. Now in beaker A, remember we have silver is 1 molar and chloride is 4 molar. We have a little more space on the next page. So in beaker 1, remember the concentration of silver is 1 molar and the concentration of chloride is 4 molar. And our KSP is equal to the concentration of silver times the concentration of chloride. So what is that going to equal here? 1 times 4 equals 4. In beaker B, situation B, our silver concentration, we have 2 silvers still dissolved, so that's 2 molar. And we have 2 chlorides still dissolved. So that is 2 molar. And if we calculate our KSP, which is silver times chloride, we get 2 times 2 is equal to 4. So Over here, KSP is equal to 4. Over here, KSP is equal to 4, because these are both saturated solutions. Are you guys okay with SATD for saturated? Okay. They are both saturated solutions. They are both at equilibrium. But because we did mix and match, the ion concentrations do not have to be equal to each other. They can if we happen to mix them like in identical proportions, but they don't have to be proportional to the coefficients. It actually made me a little sad that I had to make the concentrations over on the right-hand side equal to each other. In order to not do it and still have something equal to a nice number, I would have had to make the diagram way, 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 way bigger. Okay, because 4 is kind of the smallest number you can make. All right, so anyway, there we are, whatever. I mean, I could have gone with 6, and then I could have had 2 and 3 and 1 and 6, but then I'm drawing a bigger diagram, right? And I just, it would not fit on the page, and I'm like, fine, whatever. Now, remember, in an equilibrium, KEQ, or in this case, KSP, is always constant unless you change the temperature. In an equilibrium, do the concentrations have to be equal, or do they not have to be equal? They do not have to be equal. So if you form a solubility equilibrium by mixing two different solutions, the ion concentrations will probably not be in proportion to the coefficients. And this is our mix and match method of making a saturated solution. On the other hand, if you dump and stir, they will be present in proportion to the coefficients. Does that make sense? Okay. So if you start with a single solid and you dissolve it, the ion concentrations will be in proportion. This is our dump and stir method. Now, just so you know, no one else in the known universe calls this dump and stir and mix and match. That's a Ms. Spence thing. Okay, so if you go off to university and you start talking dump and stir and mix and match, no one will have any idea what you're talking about. They'll be like, what are you on about? Dump and stir, they might be able to figure out. Mix and match, right? There's some exercises. You're going to do those for homework, but we are going to move on to 3.2c, which is on page 35. And now we are going to be talking about solubility and LeChatelier's principle. It's back. Oh, I know, you can't get rid of it. At least not until we get to electrochemistry, and even then we kind of still use it a little bit. So solubility is the maximum amount of solute that can dissolve in a given volume of solution. You can also define solubility as the concentration of a saturated solution. Now let's take a look at what these words mean and see how these two definitions are actually identical to each other. If we say maximum amount of solute, what kind of a solution do we have? We have a saturated solution. Oh, look, maximum amount of solid, we have a saturated solution. And if we talk about the amount of solute in a given volume, what's that? That's concentration. So if we have the amount in a given volume, that is the concentration. So it means the same thing. Okay? So using this information here, can you think of some units we could use for solubility? We want an amount in a given volume. We want a concentration. We could use what? Molar. Yes. In other words, moles per liter. Yes? Huh? Grams. We could use grams per liter. These are the two that we would most often use. Okay, but you can have things like milligrams per deciliter, you know, like whatever. Let's just say milligrams per liter. Okay, or you can have grams per milliliter, etc. Now, these are the two most important ones. And in fact, in Chemistry 12, we will mostly use the molar solubility. Can you guess which one of those units is molar solubility? Molarity. The units are moles per liter, okay? Now, if you want to grab your data booklet and go to page 4, just for a second. You'll notice that on page 4, we are talking about the solubility of some common compounds. And in grade 12 chemistry, we define soluble as meaning greater than 0.1 moles per liter. So this would be the solubility. So that's the minimum solubility you need in order to be classified as soluble. All right? So this is how this relates to solubility in grade 12. University, they might give you a different set point. They might say 0.01 is soluble, whatever. Just work with what they give you. But you can see here we have our dividing line. Anything from 0 to 0.1 molar is low solubility. Anything from 0.1 molar higher is soluble. And this is the reason, this 0.1 molar is why you will so often see questions phrased like this. In fact, you might remember seeing this on your quiz. Does a precipitate form when equal volumes of 0.2 molar AgNO3 and 0.2 molar NaCl are mixed?
Yes. No. Oh, yes. Yes. Because it's still not solid. Right?
Yes.
Wait a minute. 0. That's past soluble line, right? Yeah, so yes, it's soluble. Yes, it's soluble. Perfect. Okay.
Okay.
See?
Okay.
Intelligence.
I
don't know why. I'm sure it's fine. They called me they told me I had to call the office, and I'm like, oh my God, am I in trouble? Because that's what my brain does, even though I have done nothing for which I could be in trouble. I'm like, oh my God, am I in trouble? No, it was just a former student was visiting and they wanted to know where I was. So I'm like, well, because it was period 1 and I was on my prep. Oh. All right, so and it's been a while since they've gone here, so maybe I'd moved. They saw another person in here and they're like, where is she? Anyway, so we have this 0.2 molar AgNO3. So we have dissolved 0.2 moles in 1 liter. So we have 0.2 moles in 1 liter. And same thing for the sodium chloride. We have 0.2 moles in the 1 liter. So what is the concentration of silver and what is the concentration of chloride in these two solutions? 0.2 molar, yes? And now we are going to put these together and mix them. So now we have 0.2 moles of silver and 0.2 moles of chloride, but our volume is now 2 liters. So we have 0.2 moles in 2 liters, which is 0.1 molar. Yes. Yes. What kind of a problem is this, where we have to figure out the concentration of the ions after they're mixed? No. Oh. Dilution. It's a dilution. Good try, though. All right. Now, what did we find here? We got a concentration of 0.1 molar. And where is the dividing line for solubility? For soluble or insoluble at 0.1 molar. And that's why you'll often see those concentrations listed. If you see those concentrations listed, it means use the table on page 4. Okay? All right. Yes?
Just to confirm that 0.1 molar is soluble. Because this is just a greater sign, not greater.
Do you know what? Honestly, just go with, if it's on the table, it'll precipitate. If it says 0.2 and 0.2, just... It makes me a little unhappy too, but there we are. Oh, and while we're here, let's write our solubility equilibrium equation for this. What is the solubility equilibrium equation? AgCl, solid, in equilibrium with Ag plus and Cl minus, aqueous and aqueous. And let us write a KSP expression. Silver times chloride. Now, when I dump these two things together, in that instant when I dump them together, are we at equilibrium? No. So I'm actually going to call this Q. Do you remember Q from the equilibrium unit where we're not yet at equilibrium when we use our initial concentrations? Do you remember that? Okay, so we're going to toss in the 0.1 molar and the 0.1 molar. Yes? So we have 0.1 times 0.1 is 0.01. Now, what if I were to tell you that KSP is equal to 1.5 times, or no, 1.8 times 10 to the negative 5? So What does that tell you about our ion concentrations? Are they too big or too small? Our ion concentrations are too big. And therefore, what will happen? If our ion concentrations are too big, will we form a precipitate or no? Yes, we will. If your ion concentrations are too big, it means there's not enough room at the inn. Do you know what I mean? Like you go to the hotel and there's no rooms for you, right? Too many people have tried to check into the hotel at once. And so you get a precipitate. Okay? And we'll actually do a bunch of math around this later on. All right, but that's just a preview of it. It is possible to mix silver and chloride in low enough concentrations that a precipitate does not form, and we will take a look at that in section 3.3. It'll be in the form of the Q, okay? You know, so if I had like, 10 to the negative 6 molar and 10 to the negative 7 molar, I would probably be okay and not get a precipitate. Now we get into the meat of this. This is the LeChatelier part. How can we change the solubility? Well, if we've got this equilibrium here, if we want to increase the solubility, that means we want more solute to dissolve. So if we're increasing the solubility, that means more solute can dissolve in a given amount of solvent. If that is the case, which way does the equilibrium have to shift in order for more solute to dissolve?
No.
Which way is dissolving? Right or left?
Left. No, right.
Right is dissolving. Yes, we're going from solid to aqueous as we go from left to right. So in order to dissolve more solute, the equilibrium needs to shift to the, if we shift the above equilibrium to the right, we will be dissolving more solute. And that is going to increase the solubility because we're dissolving more of the solute. So shifting right is increasing, thank you, solubility. What happens to the KSP most of the time?
Goes up. Oh.
What's K? What does K stand for?
Constant.
Constant. But KSP stays the same unless what?
Unless temperature increases.
We change the temperature. So we can change the solubility but keep the KSP the same, or we can change the temperature, which will change both the solubility and the KSP, okay? And we're gonna start by changing the temperature because it's probably the easiest situation to envision because you've probably made enough solutions in your life that most solid solutes, do they become more or less soluble when we increase temperature?
More.
They become more soluble when we increase temperature. Now I want you to think this through. Here's the reaction again. Does this mean that the dissolving process is endo or exothermic?
Endothermic. Exothermic.
So I want you to think we're becoming more soluble. And if we're becoming more soluble, are we shifting towards the ions or away from the ions?
Towards.
Shifting towards the ions. And if we're shifting towards the ions and we have increased temperature, which side is the heat term on? It's on the left side. So that means that the dissolving process is usually endothermic. Most dissolving processes are endothermic. To decrease the solubility, what would you do to the temperature?
Decrease.
You would lower the temperature, which would shift the equilibrium to the left, meaning there would be more or less calcium hydroxide dissolved.
There would be less calcium hydroxide dissolved.
Less calcium hydroxide dissolved, and therefore the ion concentrations would be lower. And therefore the KSP would be
Lower. Higher. No, lower. Yeah, lower.
What would be the effect of increasing temperature on KSP?
The KSP would go higher.
KSP increases. Are we good with that? Is that all making logical sense? Good. Now, unless you are told otherwise, you can assume that dissolving is endothermic, okay? Unless someone throws a heat term on the product side or they tell you it's exothermic. You can assume dissolving is endothermic unless told otherwise. And if that's the case, increasing temperature does what to the solubility of most salts? Increases. Solubility of most salts. Decreasing temperature decreases the solubility of most salts. So that's how temperature can affect it. Now, this is all about shifting equilibria, yes? If we shift towards the ions, we become more soluble. If we shift towards the solid, we become less soluble. We've talked about temperature. What are two other things that can affect the position of an equilibrium?
Concentration.
Concentration.
And volume in a gas.
And volume in a gas. Do we have any gases in these systems?
No.
No. So the only two things we're dealing with here are temperature, and then the other one is going to be concentrations. Can we affect the concentration of a solid?
No.
No. So off we go. Let's take a look at changing ion concentrations then. Anything that increases the solubility will shift that equilibrium to the
Wow. By increasing solubility. Right. I'm pretty sure.
Chat amongst
Okay,
yourselves.
so.
If we're increasing solubility, is this equilibrium shifting right or left?
Okay, so. Shouldn't it go left this way? It should be left. Okay, I'm gonna lock my arrows left. If CA, the arrow goes up, one will go up.
If the solubility is increasing, are you going to have higher ion concentrations or lower ion concentrations?
Higher.
And if we have higher ion concentrations, which way did we shift?
No, right.
Right.
Oh my. I was thinking about the stress or whatever it was.
It's all good. Yeah, you were thinking of the stress. Anything that decreases the solubility will shift the above equilibrium to the left. So let's think about what the stress is in these cases. And you guys need to get really good at seeing a compound, but thinking ions. So don't see the compound and think CaNO3. Think, I am adding Ca2 plus, and I am adding NO3 minus. And then I say to myself, which of those two ions has an effect on that equilibrium system? And this one should be pretty obvious, right? We've got Ca here. We've got Ca here. NO3 is just a spectator. Okay, so what have we done to the concentration of Ca? We have increased the concentration of Ca2 plus. Therefore, the system shifts which way? Left. Therefore, do we have more dissolved calcium hydroxide or less dissolved calcium hydroxide? We have less. Dissolved CaOH2. And if we have less dissolved CaOH2, the solubility has it increased or decreased? Decreased. So basically what's happening is that we have a beaker. It has calcium hydroxide. And all of a sudden we dump in more calcium. And the system says, I have too high of an ion concentration now. I am now going to shift to make a precipitate. Yes? The same, though, is going to hold true. If I have a beaker, this time that has calcium nitrate. Are you guys good? I got calcium nitrate in this beaker.
Yes.
And into it, I dump some calcium hydroxide. In this beaker over here, I got some water. And into it, I dump calcium hydroxide. So this one had calcium ion present to start with. This one had no calcium ion present to start with. Which one will I be able to dissolve more calcium hydroxide into? The one that had no calcium in it to start with. Because this one already has some ions, I cannot dissolve as much. So you can either add the calcium nitrate after you've made the saturated solution, or you can try dissolving calcium hydroxide into calcium nitrate, and that will be less soluble. Okay, so we can say CaOH2. Actually, we can say less CaOH2 will dissolve. I should put also. Less CaOH2 will dissolve in a solution of CaNO3 than in water. I'm assuming the volumes are the same, because it's already got calcium there. Some of the rooms are already taken, if you're thinking about the hotel analogy. Is good? Okay. We got to scream through the rest of this, okay? Because we have 7 minutes left. All right. Add some NaOH. This one should be fairly straightforward. Once again, do not think NaOH, think Na plus and OH minus. Which of those will affect this equilibrium? OH minus. So what has happened here? We have increased the concentration of OH minus. Therefore, we get a shift to the left. Therefore, do we have more or less dissolved calcium hydroxide? Less dissolved CaOH2. And therefore, what has happened to the solubility? Solubility has decreased. Now, you guys are going to need to think for a moment on this next one. This one's a little trickier. Is there going to be any effect? That's a great question, Dorsa. It's a wonderful question. What is NaCl going to do to this system? Does Na react with OH? No. Does Cl react with Ca?
No.
No. So, Na plus, whoa, that's a crazy, and Cl minus do not react with Ca2 plus or OH minus. They are not involved in the equilibrium. Therefore, it has no effect. So if you said, how is the solubility of calcium hydroxide in sodium chloride as opposed to pure water? It would be the same. And now you get to have fun. See if you can figure this next one out. I like it.
Okay, CL is not that. Yeah, CaOH. H could H with water. Maybe if you think something is HO, no. Yeah, exactly. So they will, isn't it a phosphation?
So you're right, the chloride is a spectator. We already determined up above it didn't do anything. Does the hydrogen do anything?
Yeah.
What does it react with? H plus reacts with OH minus, and what do we get? H2O. So what does that do to the hydroxide ion concentration? Right, because we're using this up, because it's a reactant, we're using it up and turning it into water. And just in case you're having difficulty visualizing that, if this is hydrogen and this is hydroxide, and they get together, how much hydroxide do I have left? None. So if I react the hydrogen with the hydroxide ion concentration will decrease. And if hydroxide ion concentration decreases, which way will the equilibrium shift? And therefore, do we have more or less calcium hydroxide dissolved? More CaOH2 dissolved. And therefore, what has happened to the solubility? Solubility has increased. What's going to happen with the SO4?
We have had a set of keys turned in at the office. If anybody is missing their car key, we have it in the office. Could Sora, Sonato, and First K Guard go to the career center at 3? Thank you.
That's the whole. Yeah.
Yes. Calcium and sulfate form a precipitate. Therefore, what has happened to the concentration of calcium? It has decreased. And can you guys do the rest of it? You can figure out the rest of it. I'll write it down if anyone wants to stay for a minute. Homework will be posted on Teams. It's going to be pages 38 and 39. Read them and fill them in. And then also do 3.2b. Pages 38 to 39. Read and fill in and do 3.2b exercises.
I know you don't have a set calendar. I was just wondering if next week Thursday we're doing anything because I'm most likely getting gaps.
Okay.
Okay.
I don't know.
Just asking just in case you did. It's okay.
Okay.
It's all right. Okay.
I'm glad you understand. My poor little brain just cannot
I can't blame
fathom. Right? Like I kind of go, okay, we're about here. Bam. Oh, we need to have this here. Yeah, I think we can do this one. I'll see. All right, and if anyone wanted that last little bit, calcium ion concentration decreases, therefore the equilibrium. Oh, God, I hate you. Therefore, equilibrium shifts. Right. Therefore, more CaOH2 dissolved. Therefore, solubility increases. There we go. Yay! Have a wonderful weekend. Don't come to school on Monday. Okay? Don't come to school on Monday. It's a holiday for you guys. I get to come here.
But